Hi guys, can you guys hear me?
Yes.
Okay. All right. I'm going to talk about the midterm grade for a little bit and then we'll start the lecture. And then also, tomorrow I'll be on campus from 10 a.m. to 12:30 p.m. So if you want to stop by, talk to me about future study plan, or if you want to go over the exam 2 materials again with me, or if you have any homework questions, you can stop by tomorrow. The detailed location will be announced on Web Campus today. Okay, it's going to be the computer room, the learning center, second floor on in the chemistry building. Okay. As for the midterm grade, so I finished calculating all the midterm grade. I just have to manually input all the grades on Web Campus, and I'll do that by today. Okay, and if you are in a urgent situation, you immediately have to know your midterm percentage and midterm letter grade. You can email me, but uh, manually inputting the percentage and letter grade takes a little time for me. So um, I will finish by tonight, but it will take some time. So if you need to know like right now or immediately, then email me. I'll let you know. Okay. So here is the our class's midterm performance. So um, before curve, the class average was 69%. About 8% of the students got A, 23% of students got B, 31% of students got C, 13% got D, 26% got F. Okay, and here are the number of students. So 7 students out of 93 students got A, 21 students out of 93 students got B, so on and so forth. So what I did was I curved so that the class average increases to 73%. Okay, so class average was lower upper D before the curve, but now it's in C range after the curve. So after the curve, okay, um, we have about 14% of the students getting A, a significantly larger amount of students getting B. So a lot of these students who are getting C now uh, are in a B range. Okay, um, 17 of the students got D, and less students are getting F. And I've hidden the names, and here's the how the percentage looks like. So. Um, as you can see, before the curve, 8% of students were getting A. Now 14 students are getting A. Before curve, 23% of students are getting B. Okay, they're in B range. So uh, within B, the B plus, regular B, or B minus, you might want to take a look at the syllabus. Okay, but in general, students in group letter B is 23% before curve, after curve 30%. Students getting C range going to be 31% before the curve. Now you have 22% of students getting C's. Before curve, 13% of students were getting D. Now 17% getting D, 26% were getting F, and now 17% of students are getting um, F. Okay, so if you look at the course syllabus, here's the letter grade distribution. I am going to manually input the letter grade as well, but putting a letter grade on Web Campus is a little tricky. Past experience, I've entered it, and then for some of the students were not able to find it or not able to locate it, they weren't able to see. Okay, so just in case you're not able to find where you can locate the letter grade for a midterm, midterm grade, you can just use this table, okay? Percentage will be clearly visible on Web Campus. So just in case you can't find the letter grade, you use this table. Anyone who got 92% and above will have solid A. Anyone who gets 90% above will get A minus. Anyone who gets 88% and above will get B plus, 82% and above B, 80% and above B minus, 78% and above C plus, 72% and above C, 68% and above C minus, 60% and above D. Okay, so try to look at this lower bound. Okay, so that's that, and I'm going to continue. Does anybody have any question about exam correction, extra credit, or
There are some questions in the chat.
there's some questions in the chat? Where we will be able to find the midterm grade on Web Campus. Has the curve already been applied? The curve has already been applied, but I haven't entered the grade into the system yet. I will do that by today. But again, if you need to know your midterm percentage and midterm letter grade immediately, you can email me. I will send you the percentage and letter grade right after the class. What do you mean change? Do you see any percentage on Web Campus right now? That percentage is very, very inaccurate. That's like automatic computer generated percentage adding up all the random stuff that's on Web Campus. So any percentage that you see on Web Campus right now, that's inaccurate. Okay, you will see a column that says midterm percentage, and that will be your midterm percentage. Okay. All right, somebody asks, so the current grade that's in there will be changed again after adding points we're able to earn back. Yeah, so any grade, any percentage that you see on Web Campus right now, those are inaccurate. Okay, that's just like automatic computer generation. Okay, not the calculation that I use for this class. So within today, you will see a column that says, once I finish posting the grade, I will make an announcement. Okay, so once I finish entering the grades into the on Web Campus, you will see a column that says midterm percentage, and that will reflect your midterm percentage. Okay, and there will be a column that says letter grade. Okay, midterm letter grade, but again, the entering letter grade is a little tricky. Some students were not able to find it in my previous experience. So just in case you are not able to locate the letter grade, then you use this table. Okay, percentage is going to be very straightforward. You will see it right there. Okay, but just in case you can't find the letter grade, use this table. Okay, or if you're curious, you can just email me. All right, any other questions? All right, then let's continue chapter 19. So during last class, we learned about entropy. Okay. Um, We've learned how to calculate entropy. The entropy will be final entropy. The change in entropy is going to be final entropy minus initial entropy. Okay, that's the general entropy equation that we learned. Today, we're going to move on to learning about the change in entropy of the universe. Okay, so the total entropy change of the universe can be calculated by adding change in entropy of the system and change in entropy of the surroundings. Okay, and the second law of thermodynamics states that This is second law of thermodynamics. The entropy of the universe is always increasing. Okay, any spontaneous process increases the disorder of the universe. Okay, that's the second law of thermodynamics. So because any spontaneous is reversible, as we learned before, any spontaneous process is reversible, we have expression, the change in entropy of the universe larger than 0 for irreversible process. Okay, for any reversible process, oops, sorry, my bad. Okay, any spontaneous process is irreversible. I'm sorry. Okay, so we have expression the change in entropy of the universe change in entropy of the universe larger than 0 for irreversible process. Okay, for any reversible process, okay, there's no change in the entropy of the universe. Okay, let's move on to molecular interpretation of entropy. Okay, a physicist named Boltzmann, okay, provided an interpretation of entropy at the molecular level. Okay, molecular level. And if we look at the diagram over here, when two molecules of gas are contained on the left side and prevented from flowing to the other side by this stopcock over here, once this stopcock is opened, the gas molecule will freely travel to the other side, and there are 4 possible ways that gas molecules can end up being located in. Okay, since molecular motion is random, all these 4 arrangements are equally likely. Okay, so the probability that each molecule is in the left flask, probability that each molecule is in the left flask is going to be 2 out of 4. Okay,
Professor.
go ahead.
So they're equally likely because they're spontaneous?
They're equally likely because um, gas molecule they travel freely, not because they're spontaneous. The gas mole
Okay.
so gas molecules will freely travel once you open the stopcock.
That
Two
makes sense. Thank you.
two molecules. Mm, not 2 molecules, each molecules. Can you guys make this change on your slide? Each molecule in the left flask. Okay, it's going to be 2 out of 4. Oh, my bad. I'm sorry. This is going to be both. Both. So the probability of each molecule being on the left side is going to be 2 out of 4. 2 out of 4, which is 1 over 2. Okay. The probability that both are in the left flask, okay, is going to be 1 over both molecule on each side, not left flask, I'm sorry. It's a mess today. Both molecule in each side in the flask is going to be 1 over 2 square, it equals to 1 over 4. Okay. So let's say if we have 3 gas molecules instead of 2 over here, then the chance that all 3 are in the left at the same flask is going to be 1 over 2 times cube is going to be 1 over 8. Okay, so that's having 2 molecules or 3 molecules, but instead of 2 molecules, 3 molecules, if 1 mole is used, how many number of molecules do we have in 1 mole? If you can recall from General Chemistry 1, 1 mole contains Avogadro's number of molecules. So then if you raise to the power of Avogadro's number, the chance is 0. Okay, so this tells us that in case the chance of all of these molecules to be all in the left flask is basically 0. So if you open the stopcock, all of these molecules will flow out, none of them will stick on the left side. None of them will stay on the left side. Okay. So the diagram is showing the expansion of gas when the stopcock is open. The most probable arrangement of gas molecule will be approximately equal molecules on each side. Equal molecules on each side. Okay, that's going to be the most probable arrangement. Okay, so from this, we can say that it is entropically favored for the gas to spontaneously expand and distribute between the 2 flasks. The resulting increase in number of possible arrangements is an increase in the randomness, increase in the disorder of the system. So thermodynamics usually looks at the macroscopic properties, bulk properties of the substance, such as entropy, enthalpy, energy, and heat. Okay, the bulk properties they're talking about here is entropy, okay, but what we have just seen in previous slides are in a molecular scale, okay, number of gas molecules. So how do these macroscopic properties and the molecular scale, how do they relate? Okay, to connect the macroscopic and microscopic description of matter, the scientists developed something called statistical thermodynamics. They came up with the statistical thermodynamics. So in this statistical approach, we use statistics or probability to link the microscopic and macroscopic world. Okay, so the example that we observed in the previous slide gave us a good idea how the number of possible arrangements helped explain why gas expand. Okay, there were increased number of possible arrangements when stopcock was opened. from here to here when the stopcock was open, there were increased number of possible arrangements. This means that because this increase in possible arrangement of molecules, this indicates random increase in randomness, increase in disorder of the system. So we call this possible arrangement of position and kinetic energy of molecules microstate. Possible arrangements of positions. We call it microstate. Okay, so the microstate is a term used to describe different possible arrangements of molecular position, kinetic energy at a particular thermodynamic state, or in other words, you can also say measure of number of arrangements of the atom in a system that we can have. Okay, so when the stopcock was opened, the number of microstate increased. Okay, the number of possible arrangement of molecule has increased. We say the number of microstate increased, and therefore increased the entropy. I'm going to write that down here. Okay, so to sum up this slide, increasing microstate will increase the entropy. Okay, how can we increase the microstate? How can we increase the possible arrangement of positions? How can we increase the number of arrangements for molecules? We can either increase temperature, or we can increase the number of molecules, increase volumes. Okay, these factors will increase the number of possible arrangements or increase the microstate of a system, and then eventually increase the entropy. Okay. So the letter W indicates microstates. The mathematical relationship between entropy and microstate is also developed by Boltzmann, and it is entropy equals to K is the Boltzmann's constant. Joule per Kelvin, okay, in Kelvin, times Boltzmann's constant times natural log of number of microstates. Okay, this is the number of microstates available. Okay, so for example here, how many possible arrangements are possible? 4 different arrangements are possible. Okay, so we say 4 microstates for this. Okay, so since we've learned that change in entropy is final entropy minus initial entropy, if we if we rearrange, okay, if we substitute if we substitute this equation into here, and if we rearrange, we will get this equation. This math also explains why increasing number of microstates results in increase in overall entropy. Okay, if the final entropy is larger, okay, then the change in entropy will be if the final entropy is larger, then the change in entropy will be positive, which indicates overall increase in entropy. Okay. Final microstate larger than final entropy is larger, then in result, the change in entropy will be positive. Okay, so that's why increasing microstate or higher microstate is related to increasing entropy. Okay, it makes sense mathematically as well.
Professor, can you go up a bit? Sorry.
Okay.
Got it. Thank you.
Mm-hmm. Oh, you're done?
Yes.
Okay. So again, increase in microstate will increase in entropy. So how can we increase microstate? Or what causes increase in microstate? What causes increase in the number of possible arrangements? Okay. There are three factors that we can change. We can increase the temperature, we can increase the number of molecules, or increase the volume. Okay, these factors will increase the number of possible arrangements, increase the microstate, and in result increase the entropy. Okay, so let's take a look at why increasing volume increase entropy. Because if we increase the volume, there are more available space and positions for molecules to be located at. Okay, and therefore this results in more possible arrangements of molecules because there are more available space now. Space or positions. Okay, more available space and positions for molecules. Okay, so molecules can be here, can be there, all over the place. Then because of this increase in space, now you have more possible arrangements of molecules available. Okay, in other words, you have higher microstates, both which in result will increase the entropy. How about increase temperature? Okay, if we increase the temperature, the average kinetic energy of the molecule will increase. Okay, if the molecules at increased temperature, at higher temperature, the molecules are now going to move at much higher speed, which will result in greater distribution of molecules because they're now moving so fast, moving at higher speed. Therefore, because of this greater distribution of molecules, you are going to have higher microstate and higher entropy. Higher speed, molecules are now going to travel, move around at higher speed. And because of those high speed molecules moving at high speed, you're going to have greater distribution of molecules. Then you will have more possible arrangements of molecule possible. The third factor that we can increase the microstate is the number of increasing number of molecules, right? Increase number of molecules, increasing microstate. Why? Okay, but why? This is because of the molecular motions. Okay, if you have more molecules, there are more possible positions of molecules. Since molecules never stay still, the molecules are constantly in motion. Okay, so if you have more molecules, of course, there are more possible positions that molecules can have because they're continuously moving. Okay, it's almost like if you have more people in the party, and if people are constantly in motion, if you take a group picture of them, people can have various combinations of positions at a particular time. So if you take multiple photos, all of those pictures will look different because of the various combinations of those positions. Okay, so same for the molecules. If you have more molecules, that you have more if you have more molecules, you will have more various combinations of positions available due to the active molecular motions. Okay, and there are three different types of molecular motions. The molecules can have translational motion, vibrational motion, and rotational motion. Translational motion is a movement of entire molecule from A to B. Okay, so if your molecule was here, point A, okay, it travels to position B. Okay, that's translational motion. The entire molecule is moving from one place to another place. Okay. Vibrational motion is a periodic motion of individual atoms within a molecule. Okay, so the entire molecule doesn't really move, but the atoms within the molecule, they shake and they vibrate. Okay, so as you can see over here, these atoms, okay, attached to another atom, this entire molecule doesn't move, but these atoms connected to this atom, they vibrate, okay, they shake sideways or um, sideways, and motion is called vibrational motion. The third type of motion the molecule can have is rotational motion. Okay, so rotational motion is a rotation motion of molecules about its own axis. This is spinning about its own axis. Okay, this will be a very good exam question. Okay. So to sum up the factors that increase the microstate, increase the possible arrangement of molecules, we have increase in temperature, increase in volume, okay, increase in the number of molecules, okay, or increase in number of independently moving molecules. So what happens if you increase the microstate? If you increase the microstate, you increase possible positions, possible number of arrangements of molecules, and that will increase entropy. Okay, so increasing microstate can be considered as increasing the chaosness, increasing the disorderedness or randomness of a system. Okay. Chaosness, increase, or scientific term, increase in entropy. Okay, so entropy increases as molecules have more freedom of motion. So between gas, liquid, solid molecules gas molecules will have most freedom in motion, okay, followed by liquid molecule, and solid molecules will have the least freedom in motion because they are confined. They're locked in a rigid environment. Okay, so therefore the number of microstates follow the same order. Okay, and therefore entropy also follows the same order. Entropy is highest in gas molecule, followed by liquid molecule, and solid molecule will have the lowest entropy in the system. Okay, so if the state of molecule is changing from solid, liquid to gas, okay, you will have more freedom of molecule in gas state, larger number of microstate in the gas state, and higher entropy in the gas state, right? If you are going from solid state to liquid, you are also transitioning to higher entropy, okay? More freedom of molecule, more microstate, more number of microstate, higher entropy. If you increase the number of gas molecules, this will also increase in higher entropy. Higher entropy. Okay, if you increase the number of molecules. And we already discussed why increasing the number of molecules causes the higher microstate and higher entropy, right? So let's take a look at this diagram depicting what we just discussed in the previous slide. So in the solid state, if you focus over here, in the solid state, all the molecules, they are locked in a rigid platform. Their molecular motion is very, very restricted. So the translational motion is not quite available. Translational motion is moving a molecule from point A to point B, right? Okay. So this translational motion is impossible. Okay. So the only molecular motion that's available is going to be probably vibrations. Okay. And rotations will probably not be available because they don't have enough space even to rotate. Okay, so therefore the number of microstate is smallest in the solid state. Okay, and therefore solid state has lower entropy compared to other states. Let's take a look at this liquid state. Now, in liquid state, molecules have slightly more freedom and a little bit more space to move around. They can probably make some translational motion now. Okay, no translational motion. Rotation for liquid. Now, translational motion is probably available. Okay, and because they have more room and now they have a little bit more space over here, they have more room to vibrate and rotate. So both vibration and rotational motion are available. Okay. So therefore, number of microstate in liquid is higher than solid state. Liquid state has higher entropy than solid state. Okay. And as for the gas states, now molecules have complete freedom to go wherever they want. They can totally make translational motions. They are completely free to vibrate and rotate, and therefore number of microstate is going to be highest in the gas state. Therefore, gas state has highest entropy among all states. Okay. For the diagram, it's showing a case where a number of gas molecule reduces in a chemical reaction. Okay, so as you can see, when you're performing a reaction between nitrogen monoxide gas and oxygen gas to make nitrogen dioxide gas, the number of gas molecules decreases from, you have 3 moles here, 2 plus 1 is 3 mole gas, and you're going to 2 mole of gas. Okay, and as you can also see from the diagram that the number of molecules significantly decrease, okay, because of the new bond formation. So, due to the decrease in number of molecules, less motions, less possible arrangements are available in the second flask, the product flask. So therefore, what would happen to the entropy? The entropy would decrease. Okay, you have more molecules, increase in entropy. Now you're generating less mole of gas, less molecules, so your entropy decreases. Okay, and for the last diagram, this is showing what happens when ionic solid dissolves in water. In aqueous solution, okay, dissolves in water. Okay, so ionic compounds such as potassium chloride dissolve in water, will completely dissociate into potassium and chloride ions. Okay, these ions now before before dissolving, they are in rigid they're in a rigid solid state. Okay, these are the ionic compound, ionic salt. Okay, they're in a solid form where the molecular motion was confined, but now they're in dissociated form. These ions are now have more freedom compared to when it was solid state. But what happens to water molecule is that due to the polar interaction, some of the molecule, these red and white, these are the water molecules. Some of the water molecules would surround the ion, and these molecules are sticking to the ions, and actually these water molecules are actually in more ordered state than compared to when they were in completely liquid state. Okay, so the ions are more free. They're more free to move around compared to when they were in the solid state. Okay, more disordered. However, water molecule, now they are less free to move. Less free to move around. They're in more ordered state. Okay. However, the overall net result is disordering process when ionic compound dissolves in water. The freedom of these ions, okay, they usually dominates within the system. Okay, so ionic compound dissolving in water would in general result in larger number of microstates with higher energy. Okay, but if you look into detail, is water going to have more freedom, less freedom? It will have less freedom. Why? Because of the polar interaction, these smaller molecules is going to be bound, it's going to surround these ionic ions. Okay, so again, this would be a very good exam question. Okay, let's try a sample exercise to predict whether the entropy of these processes increases or decreases. Let's try to predict whether the delta S, okay, is positive or negative for these processes. So for A, you're going from liquid water to a gas water. Okay, If you are going from liquid water to gas water, that's evaporation, okay? Due to the phase change from liquid to gas, we know that the number of microstate increases, right? And causes the increase in entropy. Delta S is going to be positive, okay? You're going from liquid state to gas state. Higher increase in number of microstate, increase in entropy. Delta S is positive. Okay. For B, the ions dissolve in water, okay? They're in aqueous state. These ions are free to move, now becoming solid state. Since these ions in aqueous solutions have more freedom to move around compared to the solid state, the microstate decreases, causes decrease in entropy, therefore delta S is going to be negative. Ions in aqueous solution have more freedom to move around compared to solid state. Okay, so therefore decrease in microstate, decrease in entropy, delta S is going to be negative. Question C, the reactant side has gas molecules which have more freedom to move around, and on the product side you only have rigid solid iron 3 oxide. Okay, the number of microstate in the reactant side is higher due to the presence of this gas molecule. Okay, so if you're going from this to this, the microstate decreases, causes decrease in entropy, delta S is going to be negative. Reactant side has gas molecules which has more freedom to move around. Okay, therefore number of microstate decreases, decrease in entropy, delta S is going to be negative. Okay, you're performing a reaction, you're combining two gas molecules into one gas molecule. The number of gas molecules in the reactant side and product side are they different or equal? 1 mole plus 1 mole, 2 mole, 2 mole. So you're going from 2 mole of gas to 2 mole of gas. There's actually no major change in the number of gas molecules. So the delta S is going to probably going close to 0. Okay, because there is no significant difference in change in number of gas molecules. The change in microstate is probably 0. Change in entropy is probably close to 0. Okay, there's not much change in entropy, probably. Okay, so therefore delta S is going to be close to 0.
Professor,
Close to 0. Yeah.
could we say that delta S is neutral?
Delta S is neutral. Delta S will have a positive value or negative value, so it's more appropriate to say close to 0 than the neutral.
Okay, that makes sense. Thank you.
Let's try another sample exercise. In each pair, choose the system that has greater entropy and explain your choice. So, question A, you have 1 mole of sodium chloride solid versus 1 mole of hydrochloric gas. Okay, of course, gas would have higher entropy, right? Gas will have higher entropy. Why? Because of the difference in the states, right? Gas states have higher microstate, higher entropy. Okay. Question B, you have 2 mole of HCl gas versus 1 mole of HCl gas. Okay. Which one's going to have higher entropy? 2 mole of gas, right? More molecule. More number of microstate. Increase in entropy. C, you have 1 mole of hydrochloric acid gas versus 1 mole of argon gas. Okay. Between 1 mole of, this is molecule. Is this molecule? This is not molecule, this is atom. This is, okay. So between molecule and atom, molecule will have higher entropy. This is because molecules are able to rotate and vibrate, but atoms cannot, okay? Okay, let's say this is hydrogen and this is chlorine, okay? Due to this bond, the linkage, that's how the molecules vibrate and they rotate and all of that. Okay, but argon by itself, it's not going to uh, vibrate and rotate. Molecules can rotate and vibrate, but atoms cannot. Okay, atoms can probably move from one location to the other location. In other words, they can have translational motions, but because they don't have this bond linking 2 or 3 atoms together, they're not molecule, right? They're the rotational or vibration motions are not quite likely to occur. Okay, so I've decided to give out some tips for the exam for those students who attend the lecture regularly. Okay, those who attend the lecture, I will tell you guys what type of problems are more likely to be on the exam. Okay, and I'm only spilling the hint for those who attend the lecture, and that these would be a very good multiple choice exam question for exam 3 coming up. Okay. All right, now that we have learned enough about microstate, and what causes the entropy to increase, we will now move on to discuss about the relationship between third law of thermodynamics and entropy. Okay, we've done with the second law of thermodynamics, and we're going to move on to third law of thermodynamics and entropy. Okay, according to third law of thermodynamics, the third law of thermodynamics states that entropy of pure perfect crystalline substance at absolute zero is 0. Okay, so the entropy entropy of pure crystalline substance at this temperature, okay, is going to be 0. The entropy is 0. Okay. For example, ionic compound at temperature of absolute 0 this is solid, right? Or a crystal. Ionic compound at temperature absolute 0, 0 Kelvin. Okay. According to this law, this compound, this crystal, has absolutely no disorder. It is perfectly ordered, perfectly flawless. Their motions are perfectly confined, restricted in a rigid environment. Therefore, entropy is 0 according to this law. Okay, there's no disorder, no randomness. Okay, ionic compound at 0 Kelvin has absolutely no disorder. Okay, perfectly ordered. Okay, motions are completely restricted. Due to these reasons, this type of crystals are considered having no disorder, no chaosness, entropy 0, according to the third law of thermodynamics. Okay, and this makes sense according to the entropy equation that we learned in the previous slides too. According to Boltzmann, entropy equals to Boltzmann's constant times a natural log of the microstate, right? Since perfectly ordered crystal would only have one possible microstate, okay? Perfectly ordered crystal will only have one possible microstate. No other microstate is available because it's perfectly rigid and locked, right? If you plug in one for the one possible microstate, the entropy, this math equals to 0. Okay, so it makes sense mathematically as well. Okay, perfectly ordered crystal would only have one possible microstate or one possible arrangement. Okay, so therefore, if you plug in one, it makes sense mathematically as well. So then any temperature above absolute 0 will have some sort of disorder according to this law. Okay, so at absolute 0 Kelvin temperature, the S is 0. This is entropy versus temperature. At temperature 0 Kelvin, the entropy is 0. Okay, look at this point. Using this S equals 0 as a fixed point, or using this as a baseline, okay, using this as a reference point, lower bound, okay, this is the lower bound. Any disorder caused will be added to the absolute entropy. As you increase the temperature, the entropy increases. As you can see, as you increase the temperature, the entropy increases. So scientists came up with crazy math to calculate the entropy values by measuring the heat capacity of substance varies with the temperature, but we do not need to know that math in this course. Using that equation that they came up with, they measured the entropy of various substances at 298 Kelvin. Scientists, they measured entropy at 298 Kelvin. This is room temperature. Okay. Using what? Using the heat capacity of substances. Okay. They got the hint from this this experiment, this graph. Okay. But what equation they use, we don't have to know for this course. Okay, we don't have to know that math. We just have to know that thankfully they measured it, and then they came up with a table. Okay, these organized values are in the table, appendix C, I believe. Let me see what appendix contains these values. Yeah, appendix C. Okay, so in appendix C, the measured values of entropy at room temperature are listed. Okay, but we're going to see the table in a little bit. So since the reference for entropy is absolute temperature, okay, this is a reference point, right? This is reference for entropy's absolute temperature. This is a lower bound. The entropy values of elements at room temperature, can it be zero? It just cannot be zero. It has to be higher than zero, right? Any temperature above 0 Kelvin, such as 298 Kelvin, will have entropy value higher than 0. Okay, so that's what this sentence is talking about. The entropy values that they calculated was molar entropies for substances in standard states. Okay. So, oops. What's a standard state? Standard state. Okay, here means 1 atmospheric pressure. Okay, so the standard molar entropy okay, is denoted as S naught. Okay, again, the table that we're going to see just in a little bit, the entropy that they calculated was molar entropies for substances, okay, at standard state. So we just call it standard molar entropy, or we also call it standard entropy. So, okay, standard molar entropy, the change here, I don't know why they put, okay. Can you guys please make correction? Not enthalpy. I made a typo. Entropy. Okay.
Dr. Lee,
So, yeah.
what does it mean by when it says be careful of size?
Oh, yeah. Cross that out too. Okay. So change enthalpy to entropy and then cross out be careful of size. So Standard molar entropy of gases are greater than liquids and solids. Okay, that's what we've discussed so far, right? Standard molar entropy increases with increasing molar mass. Molar mass, okay? And standard molar entropies increase with the increasing number of atoms in the formula. That's what we already discussed, okay? So this is something new. Okay, please make changes from enthalpy to entropy and then cross out the be careful of size. So here's a table. So they did the math, they came up with the math for us, they did all the measurements for us. Here's a table listing the standard absolute entropies of different elements and compounds, okay? You don't have to memorize this table, okay? If there's any question, you have to use these values, the table will be given to you on the exam. So entropy is a measurement of element and compounds disorder, right? So by now you might question, it's pretty crazy that scientists were able to come up with the numerical values to determine the degree of disorder, but here we go, they did it. Okay, so these are the numerical values to represent how much chaos, how much disorder they are. Okay. These are the numerical values to determine the degree of disorder. So chemistry is all about chemical reactions, right? And scientists came up with those numerical values for enthalpy here in order to be able to use in the chemical equations to find the standard entropies of products and reactants. Okay, and here's an equation to find the standard entropy change for a reaction. The entropy change in the chemical reaction, okay, the standard entropy change in the chemical reaction equals to the sum of entropies of the product minus sum of the entropies of the reactants, okay? Where N and M are the coefficients in the balanced chemical equation. Don't forget this. Okay? Let's try a sample exercise. Calculate the change in standard entropy of the system. Okay, for the synthesis of ammonia from nitrogen and hydrogen at room temperature 298 Kelvin. So it says 298 Kelvin room temperature, so we can use this table because these values are measured at 298 Kelvin. Okay, we need, in order to calculate the standard entropy of the system, we need to use the equation that we just learned in the previous slide. So now all we have to do is plug in the standard entropy values of the products and reactants using the table 19.1, or there are table 19.1, or there are more standard entropy values in Appendix C. Okay, so let's plug in the numbers. As for the product, we have ammonia. Standard entropy of ammonia is 192.5 joule per mole Kelvin. As for the reactants, we have nitrogen and hydrogen gas. The entropy values are 130.6 times 191.5. Okay, let's plug in these values. Don't forget the coefficients. Okay, for the products, we have 2 for the coefficient. Okay, 2 mole times 192.5 joule per mole Kelvin. Skip the unit. Okay. minus the reactants. As for the reactants, you have 1 mole of 191.5 joule per mole Kelvin plus 3 mole times 130.6 joule per mole Kelvin. Okay, so this is the product. This is the reactant. If you do the math, you get negative 198.3 joule per Kelvin. Okay. Where did the mole go? The mole unit cancels. Okay. So you have joule per Kelvin. All right, so that's the end of today's lecture. I'm going to hang around for another 5-10 minutes just in case anybody else have questions. Okay. Oh, another announcement. The chapter 19 homework has been postponed to April 10th. Okay, so I believe chapter 17 homework is due this Sunday, so just focus on that. Yep, April 3rd, which is this coming Sunday. Chapter 17 homework will be due. Okay, and chapter 19 homework deadline is postponed to April 10th.
Professor,
Uh-huh.
I have a question about slide 12.
Slide 12. Okay. Mm-hmm.
So I understand how you got 1/4 because there's only one way for two molecules to be on the left flask. But how did you get, I mean, why would you do 1/2 to the power of 2? Do you
1/2.
have to do it like that?
Hold on, let me see.
I know it equals 1/4, but I don't know, why would you put to the power of 2? Like, does it symbolize something?
Molecule.
Oh, because it's two molecules in the
Yeah.
flask.
Yeah.
Okay, that makes sense.
Oh, did I not explain that? Okay.
I don't know, but my
So,
mind went.
yeah.
Yeah.
So this is the number of molecules. Okay. So that's why if you have large amount of molecules, such as Avogadro's number of molecules, for example, if you take 1/2, the probability raised to the power of Avogadro's number, that's going to be a very, very number close to 0, right? So that tells us that the probability that this large amount of molecules to be on one side is basically 0. Okay, so this probably tells us that when you open the stopcock, this large amount of molecules will most likely flow out. There is very low chance that all of these molecules will stay here when the stopcock is left open. Does that make sense?
It does. What
Yeah.
about the other 2 on the denominator? Does that represent that there's 2 flasks?
What's that again?
For the number 2 on the denominator?
Number 2 on the denominator. Here?
Yeah. For that one, does it represent that we have 2 flasks? Or is it always going to be 1/2?
2 flask.
Yeah, we have 1 flask on the right and 1 on the left.